Okay, so the next topic we're going to discuss is pressure vessels, and this is relatively going to be an easy topic to go over. Uh, Pressure vessels are essentially a special case where you can turn something that would look like a 3D problem into a 2D plane stress problem just by making that primary assumption plane stress. Oops, hold on. Just by making that primary assumption plane stress, we can simplify the problem into a more coherent and easier set of equations we need to solve. So to begin with, we have a traditional pressure vessel here that has an internal pressure P. And we will just go ahead and look at the midsection of the pressure vessel. We will take a sum width dx from the middle of the pressure vessel and then take an element from that on the surface of the pressure vessel. And the element would have the following stresses. It would have what would be known as the axial or longitudinal stress that goes along the longitudinal or longest dimension of the pressure vessel, and the hoop stress, which goes radially or circumferentially around the surface of the pressure vessel here. Okay, so once we make this plane stress assumption, we can easily simplify the problem. Another thing to note is that typically pressure vessels don't experience shear stress since the expansion is uniform, and the expansion doesn't really challenge the change or the shearing of each internal surface element to one another. It's more expansion or normal distribution of pressure. We only assume normal stresses for now. Okay, so we have two types, axial and hoop. Now, how do we derive the axial or hoop stresses here? So starting off with axial, so I cut that pressure vessel in the middle. So here's the pressure vessel here, and it has thickness T for wall thickness. The axial stress will act as a resultant here from the thickness of the walls as such. So this would be sigma A, so axial stress, all right? So the pressure can be modeled as follows. Essentially what we consider is that the pressure acts on the face plus the thickness of this of the internal pressure vessel here. And essentially what happens is we consider the active pressure all the way to the back wall and superimpose that onto this face here. So we have basically a pressure that acts on a circular plate. So pressure P here, okay? So now we go ahead and do the free body diagram of this. So you basically do some forces in the axial direction, okay? So with some force in the axial direction, we start off with this. The axial stresses here can be written in force terms by multiplying it the circumference of the pressure vessel, and the radius of the circumference is typically, what people usually choose is a nominal radius since the thickness is typically much smaller than the radius of a pressure vessel. So they would either choose a center from the center to midsection of the walls, or they would just choose a appropriate radius that would reflect or wouldn't be negligible when you compare those two quantities. So there's that, and multiplied by T here, T considering the thickness. So that's basically right here, the area of that wall. And that will essentially equal the pressure, effective pressure happening in the pressure vessel, times the area of that effective circle there. So pi r squared, okay? Now you just rearrange these terms, and again, we'll just go ahead and throw this in. T is significantly less than R. We will get the following. The stress in the axial direction is the pressure times the radius divided by 2 times the thickness, okay? And that is axial stress in the pressure vessel. Okay, so now we go into hoop stress of a pressure vessel. Same thing, there's a resultant stress happening on the thickness of the wall. So here what we're doing is we're taking the pressure vessel and we're cutting it half straight down the middle, perpendicular to the longitudinal direction here. So splitting it down the middle, we get a resultant hoop stress here, okay? So how we model the pressure then is, again, we superimpose that as a face that's essentially acting on this whole face right here as a singular, either square or rectangular shape here, and go ahead and draw the pressure acting on it. The next thing we do is now we just sum forces in the hoop stress direction for this model here. I'm going to go ahead and just write it out. You're going to get the following. So 2 times the hoop stress, considering top and bottom walls, times the thickness, times dx, the whatever arbitrary section of the pressure vessel we're taking in the longitudinal direction, equaling the pressure itself times 2 times r dx. Okay, so very self-explanatory. If you rearrange everything, you get the following. Hoop stress is equal to pressure times the radius divided by thickness. Okay, and that is hoop stress. And from this derivation, it's fairly clear that the hoop stress is twice that of the axial stress. So that's a little thing to just remember as a shortcut if you just want to calculate one of these and remember this relationship here. So moving on, if we want to do something like spherical or sphere pressure vessels, so essentially what we would do is first we would model it. We would take half a sphere. We would take half a sphere, just like this. And just pretend that's half a sphere. And again, the thickness is much smaller than a radius. I know that doesn't look like it here, but I'm just like over exaggerating this image. We have a reaction axial stress here. So the derivation is actually the same for axial stress derivation here. It would yield the same equation. Now the thing is, if you go ahead and split it perpendicular to this plane here, what you would get is you would get the same exact model. So in this case, the hoop stress equal to the axial stress, equal to the axial stress. Let me draw that better. Which both at this point would equal pressure times radius divided by 2 times the thickness. Okay, so that's what you would do for spherical pressure vessels. Okay, and that's it for pressure vessels. So okay, where's the next part? There it is. So the next thing to discuss is the thermal stresses. Thermal stresses, okay, let me restart that. The next topic of discussion, the next topic of discussion is thermal stresses. So thermal stresses, relatively easy. The only thing we need to note here, at least observe for our initial assumption for thermal stresses, is that the primary effects and kinematic effects is observed to be expansion. Okay, so if you heat something, you expect it to expand. So let's go ahead and let's just do a 1D case for now so you can have a clear glimpse of what's going on, how that relates to the stress and strain of a material. So one dimension here. Okay. For a one-dimensional case, let's just take a simple block that is fixed on one end, and we heat it up. So there's an invoked delta T onto this system here. And what happens, you'll expect the block, so in the x direction here, to expand by this much. Okay, so the block was originally length L here. The expansion, we would probably give it the term delta L, okay? And you guys probably remember this from your mechanics of materials. That delta L there will be equivalent to L times alpha times delta T, where alpha here is the thermal coefficient of expansion and delta T here is the change in temperature. And this quantity right here is usually a constant. So if you guys basically divide the length here on both sides, so delta L divided by L here, what we'll get is we'll get the strain in the x longitudinal direction, which would equal alpha delta T. Okay, so basically we've established a relationship that the strain is directly impacted by the thermal coefficient expansion and change in temperature. So what would happen though? We have that same block that's fixed on one end, but the other end is also fixed too, so it can't expand like this. Well, it's simply now in compression, so that would mean, since there's no expansion, epsilon x is 0, there must be an internal stress, and then internal stress you'll find is negative, since it's a compression, alpha delta T times the Young's modulus from your mechanics of materials class. All right, so we're going to go ahead and write a full constitutive model to derive this, so you'll see how we get to these presumptuous equations here. So from the constitutive model, go ahead and put that in. All right, so from our constitutive model here, if everybody remembers, there is our strain vector, which equals our compliance, or sorry, yeah, this would be the compliance matrix. Actually, if it was compliance, it wouldn't be, for completeness sake, if it was compliance, it wouldn't be C, it would actually be S. Okay, here's our compliance matrix times our stress vector here. Now, the expansion, as we addressed before, is contributed by the thermal coefficient times the change in temperature here. So this expansion term, the strains, must be also complemented by that phenomenon, which we've observed empirically and theoretically, alpha delta T. And again, this quantity can be a constant. Just know of that if there are 6 strains here, you would basically put this in vector of 6. If you basically remember how to multiply or add a constant to a vector, that's how it works. So yeah, this is essentially the constitutive model here, and this basically tells you everything we need to know to get these two formulations here. So going back into a 1D case, so we have a free end again. Free end 1D case. We established, or at least if we take this model here, we'll establish that the x direction, if there's any stresses here, it would be indicated in the model and indicated in this diagram, but there's not. So what would normally be 1 over the Young's modulus times sigma x would not be existent in this model. And all we have left is the coefficient of thermal expansion and the change in temperature. And that's it. So what about the restricted end? So for the restricted end, again, 1d. Now there is no expansion. So epsilon x is the one that goes to 0, whereas everything else, 1 over the Young's modulus times sigma x plus alpha delta t pertains. So now you just do a little bit of arithmetic, and what you'll get is sigma x equal to the Young's modulus, or negative the Young's modulus, times alpha delta t, just like how we got here. So that's essentially all you need to do for thermal stresses. You consider, or you you introduce the thermal coefficient of expansion and change in temperature term into the strain equation to solve for the overall state of the system when thermal stresses are applied. So one quick thing to note here. For most isotropic materials, the alpha times delta T term is typically constant. And this is the most important part, unless specified otherwise. There may be times where alpha delta T is an equation based off your geometry, or it might have a different material that's embedded into the problem. You also have to consider that as well. So this statement not necessarily may remain true if there is some special conditions that might alter it, okay? But with that being said, that's basically it for thermal stresses.